Welcome back, everyone. In the last episode, we implemented our borders, added the gravitation back, and changed the calculation of the bounciness in our collision resolution. But we still have a problem, which we encounter quite a lot in the last episodes, and this is this sliding into each other, and we're going to tackle that today. But first, I want to change something to the simulation class again. And this time we're gonna again change our shapes. So we have kind of a stacking of objects. And for this one, I think I can leave the circle. That's okay. I'm gonna add a new rectangle. So I'm just gonna copy this line, add it here. Then I'm gonna change the coordinates again. From the first one, the coordinate is now 300 by 300. Everything else is okay. Then the other rectangle will be 400 and 150. And the other rectangle again, the third one will be 200 and 0. The width of the second rectangle will be 200 by 100. And the width of the third rectangle will be 200 also by 100. Okay, both of them will have like, yeah, this mass 60, 20, 20, and the circle, well, I think it's not really important, but I'm gonna set it to 100. All right, also, let's make it a little bit bigger. All right, I think that's everything for the simulation class. Yeah, looks good. Now I'm gonna change, or I'm gonna add the positional correction right here. And the positional correction, here we're just gonna move out a shape out of each other. Right, simple. We need to set a variable, and this will be the correction percentage. And this will determine how much the body will be pushed out every time we call this method. In this example, everybody will be pushed out by 20%. And in the next iteration, it will be pushed out again 20%. If you set it to 1, it will be pushed out immediately. But this can lead to instability to the simulation, and that's why it's probably better to have it between like 5-6%, 60% to 20%. I will leave it to 20 because we don't have much objects, and the simulation still runs pretty fast. So I guess that should be a good number for that one. But of course, you can try different values and see what's happening. Okay, then we have to calculate the amount to correct. And this is a calculation from the depth. We divide the depth by the inward mass. So if we have a body which has more mass than a mass, I mean mass, if a body has more mass, then the other one will be pushed out, more than the one with the big mass, okay? And we can calculate this by this dot Ricci A dot inward mass plus this dot Ricci B dot inward mass times the correction percentage. All right, then we're going to create a correction vector. This will be the vector where we're going to move our object, and the correction A, let's say movement, is the oh, 1 second. Oh, I forgot something. Oops. Yeah, the correction vector. Sorry. Well, we need to first make a correction vector, and the correction vector is the amount to correct times the normal of the collision. So this will be the normal, as I said, this dot normal times the amount to correct. Okay. Then we're gonna calculate our specific movement vector for every body. For the rigid body A will be, I'm gonna call this rigid A movement. Will be again the correction vector, but this time scaled by -1, like in the collision resolving method, and also scaled again with the invert mass. So rigid A dot invert mass times -1, and the same for the rigid body B. There we go, and there we go. Also remove the -1. And then we need to check if one body is a kinematic. So we don't need to do this if that body will be a kinematic body. If rigid A is a kinematic body, then if rigid A is not a kinematic body, then we're gonna say this dot rigid A dot shape dot move, or we can say let's use the get shape method. Get shape dot move, and here we're gonna add the rigid A movement vector, and the same for the other one. I think I can just copy that again. There we go. Rigid A will be rigid B. This will be rigid B, and there we go. Yeah, and I think that's everything for our positional correction. I think we can try that right now. So let's go back to the browser. Refresh. There we go. We have our shapes. Let's see what's happening. Okay. Yeah, that looks pretty nice. There is no sliding anymore. The other shapes were bouncing a bit, but that's because of our material values. Here I'm going to move the other shape from the other one. Of course, we don't have a rotational impulse. That's why the shape looks kind of weird on this other one. Come on. There we go. All right. Pretty cool so far. Really, really nice. All right. Yeah, that's already everything for this episode. In the next one, I'm gonna show how we can calculate the inertia of any convex polygon. Because we need this one to finally rotate really, by torque. We need that to rotate objects by torque, and also to do rotational impulses. All right, then see you there. Bye bye.